Okay, so for the fractional moment method, we will consider the following discrete Anderson model on L2CD. Yeah, with IIT single site potentials. We will assume that the disorder is very large and that the single site potential omega x have some absolutely continuous distribution with compact support and bounded density. So these are very strong assumptions, but I want to keep the proof as simple as possible. Now, in order to get the localization results, so the pure point spectrum, the exponentially decaying eigenfunctions, and the strict dynamical localization, okay, we will work with estimates of the Green's function, okay, defined in the usual manner, like this. And the first aim will be to prove the following. So we take some s between 0 and 1 and consider the fractional moments of these Green's functions to the absolute value to the power s and its expectation. And we want that this is exponentially decaying in the distance of x and y, and we're using the one norm distance in CD. And this decay in expectation, these constants c and gamma are independent of the NHR C. C can be any value, well, not real, but complex values. So that's, there you have no problem. This inverse will always exist for non-real C. Okay, but it will be uniform in the distance to the real line, for instance. This is a very important aspect. Okay, so now in order to get this, we will look at some expressions on how we can express the Green's function in a nice way. And so first, we need some a priori estimates. And so, well, we can express using a resolvent identity this Green's function going from x to x at the same lattice side as a function of omega x will have the following form: 1 over a plus lambda omega x, where this a is actually some Green's function of some subgraph where you take out the lattice side x, and so the value will be independent of omega x. That's important. And one can do something similarly looking at this type of matrix. So this here is a fancy way of writing the matrix, okay, G of xx, G of xy, G yx, G, Y, Y of these four values of the Green's function and this matrix. So this can be expressed in this way, and you see that it's basically the same formula as here, right? Only now A is a matrix. Okay, here you have these potentials at these lattice sites. A doesn't depend on omega x and omega y. Okay, well, and if we do this and look at now this to the power s, right? And we take out a 1 over lambda to the s, then we divide the denominator by lambda to get this thing, and we integrate this over the distribution of omega x. So we take the expectation of this only over the potential omega x at lattice side x. So we have to multiply with rho of omega x, the omega x, like rho is the distribution density. Then we can take out an infinity norm of rho. We assumed it to be bounded, and so we are left with this integral over the support of rho. And then basically, okay, no matter what this value here is, we have something here that will be uniformly bounded by some constant c. Basic in the main point of the fractional moment is basically that the function 1 over x to the s for s between 0 and 1 is integrable at 0, right? So, so for this reason, the fractional moments. And okay, one can get a similar result using this formula and taking expectation over omega x and omega y. Here, one has here a uniform constant also. Over lambda s, of course, this constant a priori is different from this one, but we just take the bigger one. Okay, so we have these, we get these a priori estimates. Okay, and then now in order to get to the exponential decay, we sort of have to use them and take some kind of path expansion of our resolvent and see that we pick up a factor smaller than 1 along the path and get some exponential decay. Okay, so how is this done precisely? Well, first, actually, we will do some kind of decoupling argument. Okay, so maybe I will explain the decoupling part later. But so basically, from these matrix representation, right, that this is some kind of A plus lambda omega x omega y minus 1. Using Cramer's rule, you can find that this gxy part, okay, so it's given by determinant divided by determinant, can be expressed in this type of way. We have some alpha and some beta, and this is alpha divided by lambda omega y minus beta, and these ones are independent of this entry omega y. Okay, and so we're using this formula here. Okay, and now we are using some kind of taking out the 1 over lambda to the s the other way, and one can actually now show that the integral over 1 over this to the power s, if you compare it to the integral of omega minus some other value over this to the power s, they're kind of comparable. So there's some unique constant c prime such that this one is bounded compared to this one. And so why am I doing that one? So alpha divided by this, okay, so if you multiply with lambda another time, you get back this g. And so now inside the expectation, we have this Green's function with this factor here. And why am I doing this? So this will become clearly now in this kind of path expansion. So if we take x to be different from y, then okay, of course, the scalar product between x and y is 0, right? And then we can write it in this form. But now h minus c, we can write it as the minus Laplacian plus, okay, the h plus the potential. So we have the lambda. So when you have the potential applied to y, we have this lambda omega omega y, and then minus c. Applied to y, we have this part here, and this first part, okay, with the discrete Laplacian. So this is the sum, right, of the neighbors. So the Laplace applied to this state, right, is simply the sum over these things where this is distance 1. Okay, and so this part here, okay, gives a sum of these Green's functions from x to lattice sites u that are neighbors of y. Okay, and then this part here is equal to this. So if 0 is the sum, then this part here is equal to that. Okay, and now we continue in our argument here, this equation by taking now absolute value, power s, and expectation, okay, to the power s. So this thing then will be given by the expectation of the norm of this whole thing to the power s. But then we use that we have a fractional moment, and there is this inequality that when you take the absolute power of a sum like this to the s, it's bounded by the sum over this a into the power s of these absolute values. And so therefore, we then get that this thing is bounded by that. So we have this constant, and then we get here the sum expectation of the fractional moments of this one here. Okay, and now, okay, we have here this factor, which is small if lambda is big enough. Okay, and so what one has to do is now to iterate this argument. So okay, so we have this inequality here, and now we can iterate it for these ones, right? And how long can we iterate it? Well, as long as none of the u's is equal to y. So you can iterate how many times? Well, how many times as long as you get up to u. Okay, and so now you can ask, so what's the worst you can happen? So you have this factor c prime over lambda to the s, okay, and then you have this sum. But how many neighbors do you have for y? Okay, so you have here 2D terms. And the worst that you can have here is when you take the supremum over the whole lattice of the expectation of this fractional moment, right? So this is kind of a very brute force estimate. And you iterate x minus y times, so you have this kind of equation here. And now we have a bound for this one that's uniform, right, in all xu. So I mean it's because well, the exponential factor is at most 1, right, here. So you have a very, right, so giving the a priori bound here and here, okay, that works. Sorry. You have a bound for this supremum term, right? And then if you take lambda big enough, this here will be smaller than 1, and you will have exponential decay. Okay, so for large disorder, we find the exponential decay in this expectation of the fractional moment of the Green's function. Okay, and so now the question is, how do we get from this to localization terms? Well, it turns out that a very useful object in these arguments is what's sometimes called the eigenfunction correlator for some spectral interval I. So basically, it's a bounded variation of this type of complex measure when you go from a spectral measure when you go from lattice side x to lattice side y, right? So you take all continuous functions that are norm bounded by 1. So okay, and then you take your operator h lambda f of h lambda, and then you take the projection onto the energy interval E. Okay, apply this to the state centered at Y. Okay, take the inner product with the state centered at X and look at the absolute value of this. So this is this Q lambda. Okay, and so what one notes is, so why might it be helpful for dynamical localization and more things? Okay, so basically for the dynamical localization, we looked at this type of things, e to the minus ith, and then we applied to some initial state, which might be something located at y, for instance. Take the projection onto the interval I of this one. Okay, an interproduct with x, and then of course this thing here, okay, is of this sort, right? And this is e to the minus itx is a function that is has norm 1, infinity norm 1. So you have this for any t. So you have this one, supremum over all times bounded by this quantity. Okay. So right. Okay. So this already tells you that. Okay. So this might be helpful to have a bound on this one to get. You will get something giving you dynamical localization. And okay, so under the given assumption of the potential that we have, you can show that there actually exists some constant depending on the fractional moment you choose, such that the expectation of this quantity, and actually I'm writing here absolute value, but really it's a positive quantity, right? So the expectation of this quantity is bounded by Well, this constant CS times limit inferior when eta goes towards 0 of integral over I of this expectation of this fractional moment with e plus I eta. But then we have a bound on this, right, exponentially decay in the distance of x and y uniform on eta and e. So when you integrate over a compact interval here, you have, okay, finite integral, then you get a bound on this one exponentially decaying in the distance of x and y. Okay, and so, well, how do you get dynamical and spectral localization from this? So basically, if lambda is sufficiently big, now we can guarantee for any interval, well, actually for any bounded interval, that you find that the expectation over the supremum of all times of this quantity here, okay, decays exponentially in the distance of x and y. And then if you have some vector that has finite support, okay, it's supported on the case that have one norm, one equivalent some r, then you can look it. So remember, this was the quantity one has to look at for dynamical localization, right? Okay, and so that's basically this quantity here multiplied by the x, the norm of x to the power p. Okay, sum over all x. Okay, so you have this one, and then for any t, you have this one bounded by this. So basically, you have this constant c, and you have to sum up this point, and you multiply also, okay, by well, actually by psi of k norms squared, absolute value squared, but this is bounded by the norm of psi squared. So okay, so at the end you get this very rough estimates. You get this estimate here, and due to this exponential decay, this is bounded. Okay, and so if the expectation over this supremum is bounded, then it means that almost surely, of course, this quantity is bounded. So almost surely we have strict dynamic localization, okay, for any kind of moment p we can have here. So this is how you obtain this one. And well, then one can use the range theorem to actually get to pure point spectrum, or one can also do things a little bit differently, working again with this quantity, this eigenfunction correlator. So one can show now, if you kind of take an exponential decay, okay, a little bit smaller than the gamma we have in the theorem. So we multiply with e to the gamma x minus y, and then the correlator squared. One can actually show that these objects here will be almost surely finite using this exponentially decay bound we had before. And from this, okay, one can deduce that the spectrum is pure point in I, well, if there is spectrum, and the normalized eigenfunctions with, okay, some localization centers. So, okay, I will not talk too much about this, but basically one gets exponential decay for the eigenfunctions with this rate mu. Okay, and some constant that depends on the randomness, but it actually also depends on the localization center. So for some realization omega, it will not be possible to have here the same constant for all eigenfunctions. Actually, so one has to allow here for some variation in this. Okay. Well, so this is the part localization through the fractional moment method. Next, I want to tell you a little bit about localization in one dimension. So one-dimensional models are quite very special. And if you remember, the main point difference of one dimension and multi-dimension was that in one dimension you find localization even at small disorder. Okay, so and this is due to some very special method in one dimension, which is the transfer matrix method. Okay, now, so let me remind you for the model we are looking at right now. And here, actually, I will not use a disorder parameter because it's basically not needed. Okay, so we will look at the Hilbert space, the L2 space over some strips, so some product graph of C with some finite graph, which one can think of as a tensor product of these two Hilbert spaces. And then the operator, H applied to psi at side n will be given by, okay, minus psi plus 1 minus psi minus 1, that's the discrete Laplacian, plus then we may have some fixed matrix A, and then we have this IID random symmetric matrices omega n here. And A and also omega n are symmetric R by R matrices. Psi n now will be a vector and not just a number. So okay, so this psi n before I had written psi of x. I'm sorry for that. So a little bit a change of notation. Okay, and it's of course L2 summable if it's in this L2 space, right? And then one way to think of H is you have these block 3 diagonal matrix. Okay, infinity going to infinity on both sides. So you have on the off diagonal blocks, you have minus the unit matrix. So this is due to this part. And then here on the diagonal blocks, you have these, well, these matrix potentials, these random ones, and then this fixed matrix A. Okay. Well, and then if you look at the eigenvalue equation, right? So you write this H psi equal E psi, so H psi n equal E psi n. And you sort of resolve this equation for psi n plus 1, then you will find that psi n plus 1, put it to the other side, and put the E psi n on this side. Then you will find that it's A plus omega n minus E times psi, and then minus psi n minus 1. Right? So this is this line here of the matrix multiplied with this vector. And then you add the trivial equation psi n equal psi n, like this in the matrix here. And you get here a transfer matrix, okay, relating for a solution, a formal solution, psi n plus 1, from psi n to psi n and psi n minus 1. Okay, and you can show that actually for any energy, this transfer matrix will be a symplectic matrix. So you take its transpose, you multiply by J, T, and you get back J, where J is, I'm sorry, there's a mistake. J is the symplectic form, so it should be like this here. Okay. Now, before sending the file, yeah, I will make sure to kind of get rid of all these mistakes. Sorry. So, okay, so the main tool now are Lyapunov exponents. So what you do is, okay, so in order to get the solution, right? Okay, so you can do it actually at real and also at complex energies, but so basically you have this equation, right? And so if you fix, let's say, psi 1 and psi 0, right? And to get psi n plus 1 and psi n, what you need to look at is this product of transfer matrix, right? And then you can, and then, I mean, because the potentials were IID, all these transfer matrices are IID, okay? And now if you look at the shaped singular values, the logarithm of that, you normalize it 1 over n and take the limit, then these limits are kind of, these are kind of self-averaging quantities, and they exist almost surely and are almost surely constant, and they are called Lyapunov exponents. Okay, and then due to the symplectic structure, actually, so we have So the size, so we basically think of a strip, right? And the width of the strip is R, and then the size of the transfer matrices is sort of 2R by 2R. Okay. And so we have 2R singular values into a development of exponents, and then okay, one has some, due to the symplectic structure, one has some symmetry. So basically, they come in pairs of additive inverses, right? So for any value gamma, minus gamma will also be one of the development of exponents. Okay, and then comes into play the oscillate multiplicative ergodic theorem, okay, showing that there's a set of probability 1 such that you find a random orthonormal basis such that the growth of the norm, when you apply this to the vector Vj, is basically gamma j. I'm written of that. Okay, and this means that when you have now concrete solutions to the eigenvalue equation, that they either, so if all the gamma j's are different from 0, then they either grow or decay exponentially. And the ones that grow exponentially, they are basically not relevant for the L2 spectral theory, and the ones that decay exponentially to both sides, to plus and minus infinity on the line, that one will be square summable and will form actually eigenvectors. And so therefore you have kind of localization. So this is sort of the rough scheme, but there are some catches. It's actually not that simple. So first, one can guarantee under very general conditions for the Sanderson model on the strips that none of the Lyapunov exponents is 0. This is basically combining criterion of Goldscheidt-Margulis with some article by Goldscheidt. Okay, and then using this, you can, okay, so you can now use the arguments with eigenfunctions for half-line cuts, and Fubini argument, you can deduce the following statement, that almost surely one finds that for Lebesgue almost all energies, this sum over these Green's functions going from x to y, e plus I at the norm squared is finite. Also, if you go with the limit of this imaginary part eta down to 0. Okay, and as a matter of fact, I mean, you will get, you will have sort of also almost surely some exponential decay for these quantities when you go with the limit eta to 0. Okay, and why am I bringing this up? Because now there is a criterion from Simon Wolf. Okay, and so one can conclude, at least if the distribution has an absolutely continuous component, that you will have almost surely a pure point spectrum. So how do you do this? So basically, I mean, if you know this for the Green's functions, for some reading operator H, okay, then you can make a rank 1 perturbation argument. So you look at H plus T times this operator here in the Dirac notation, which means is the spectral projection onto the lattice side X. Sorry, not spectral projection, the projection, orthogonal projection onto functions that have only values that have support at lattice side X. Okay, and so you look at this one, and then this one, it will be for almost all parameters T, it will be pure point. So there will be no continuous component here. If you notice for Lebesgue, almost all energies in the interval AB. Okay. Right, and so now basically we take one single side potential, so it's independent of all the others, and you vary it, and okay, you see that for some positive probability you get only pure point spectrum if you have an absolutely continuous component. But then you have the almost sure constancy of the, you get, yeah, so you get for positive probability that you have localization interval AB, but then it's with probability 1 because of the almost show constancy of the spectrum for ergodic operators. Okay, so this is this part about one-dimensional methods. So they depend very heavily on these theorems coming basically from dynamical systems. Okay. Now, finally, let me also tell you a little bit about one of the proofs of delocalization. Okay, so for this, I want to look at the beta lattice and the beta strip. Okay, so remember, so the beta lattice is this kind of regular tree graph, and the strip is here make products of this with finite graphs. Okay, and we call BK the beta lattice of connectivity k+1. So that's the beta lattice that has k+1 neighbors for every vertex. So this one here is B2, and every vertex has 3 neighbors. And why do we call it B2? Because you sort of okay, so you sort of think of having a forward direction, and if you go from this forward direction, let's say into there, then you always, each point has 2 children, right? So this vertex has 2 children here, it's connected to this one here, has this parent, and then has 2 children, and so on. Okay, so this way you can think of constructing like the forward direction of this one, and then, okay, so if you do this with some root, then you have a beta lattice where you have kind of one vertex that has only okay, connectivity 2, but then, okay, you add this one here and you have the whole thing. Okay, and so the operators we consider is again the discrete Anderson models. So we have well, actually, because some formulas are better, simpler in this way, I'm now using the positive Laplace operator, but in the discrete case, minus Laplace plus Laplace is kind of not so important. Okay, I have some vertical Laplacian part in the slice of the strip, and then the random potential, or maybe random matrix potential. Okay, and now, okay, so these things are technical details. I need some moment bound on the potential, and okay, so there's some interval which will be not empty if k is big enough, the connectivity. Okay, then I can construct some set IAK such that for any compact interval here, I find some disorder such that up to this disorder, the spectrum of H lambda in this compact interval is almost purely absolutely continuous. So there's no point spectrum, there's no singular continuous spectrum, and there is absolutely continuous spectrum. Okay, so what are some proof ideas? So again, everything works with the Green's function, or in this case with the Green's matrix. So you have to maybe introduce a bit the notation. So X is a site in the beta lattice, and then K is a site in the finite graph, and I take products with finite graphs. So XK is some vertex in the product, right? So I look at all these things, and I organize them in a matrix and call this the Green matrix at site X. Okay, and I do this primarily for complex energies. Okay, and then the spectral measure at xk you can obtain as this type of distributional limit, right? It's using CV of Stieltjes transform of measures, basically. Okay, and now you can get in a relation for certain Green's functions. And here I have to introduce a little bit this notation. So basically we consider the beta lattice. Okay. And so we have here X and we look at the parent Y, right? And then when I look at the graph X and remove the connection to Y, it means that I'm sort of cutting here. Okay. And when I'm cutting here, I'm kind of left off with some rooted beta lattice that starts at X. Okay. And now when I look at these things, so what happens is, so here are the sides, the neighboring sides W to X. So when I cut off here, right, and here, so here's another W, then the tree disconnects. And I have here one beta lattice that looks exactly the same as this one here, and this one looks exactly the same as that one here. Okay, and moreover, the potentials here and here will be independent. That's kind of important later, but first, getting these connections and resolvent identity, I obtain a relation for the Green's matrices of this form, right? So you have here basically your potential sitting at X. That's kind of important, that comes in, and then your value of the forward Green's function here and here also come into play. Okay. And so you have this relation here, which is kind of, okay, so you have a sum of matrices and then you take the inverse. That's kind of something that's maybe not so good for the analysis, but then what can you do is, okay, so we define some kind of complex function where we have this function psi of g. So that's a function on the set of pairs of symmetric non-negative matrices m plus and minus, and we take the exponential of I over 2 times the trace, okay, of this combination here. And so, okay, and well, one can then use some supersymmetric formalism. I will not get too much into the details, and construct certain Banach spaces such that the map, when C of G goes to Xi to minus G inverse, so this minus G inverse appears in this expansion of the Green's function, where this is realized as a linear operator T on this Banach space. Okay, and the linearity is kind of important. And what is this T? So basically, it's a Fourier transform. And so the way you should think about this, I will maybe talk about the supersymmetric part in a bit, is the following. Okay, so if you have a Gaussian distribution and you make the Fourier transform, you get a Gaussian distribution, but the variance matrix, it becomes its inverse, right? And here we have matrices G that have a positive imaginary path. So when we multiply by I, we get something with a positive path. So it's something like a density for Gaussian distribution, and then the Fourier transform gives you another density for Gaussian distribution. But basically, this IG will convert to IG its inverse, right? So this is kind of this transform here. And the supersymmetric part is really to get somehow the derivatives into play. So I will not be too precise on this now, also due to time. But basically, so what's the main idea is, okay, so you introduce variables psi bar psi that are Grassmann variables, okay? And then when you have a function f of x squared plus psi bar psi, okay, so here you have Grassmann variables. So psi squared will be 0, psi bar psi will be minus psi bar, for instance. Right, and for a pair of real variables, you assign a pair like this, and you assign some kind of super symmetric scalar product in this way, and then when you apply this to a function, so here you have a positive value, x squared, right? Then this will be defined by a Taylor expansion, basically, right? So then, in this case, you just have a first derivative term, and so therefore the derivatives will become part in the definition of this Banach space. So they are kind of Sobolev type Banach spaces. And okay, so for matrices this looks a little bit more complicated. I will not look at that. And then there is an integral over deep psi. Is when you have when you integrate over the Grassmann variable. So you just define this as a linear operation from the Grassmann algebra for functions, right? So this integral here, so this is an element of the Grassmann algebra where you have one Grassmann variable psi, and this one is just f2. You forget about the other part. Okay, so why these things? Okay, so first of all, this recursion, so this minus and then the inverse, this is the linear operator t applied to this when we look at the function c, right? And then we have this function c of that, but this thing, so for the function c, m is in an exponent, right? We have like e to the e, e to the, okay, trace mg. So when you have a sum, then for the function c, it turns into a product. So here's the product. Okay, and now we take expectation of this equation, and then we use that when we decouple, we have here independent trees. So the expectation of these things will all be the same. And because of linearity of t, the expectation goes inside. And then because of independence of all these things, so omega x will be independent of the values here. And these potentials are independent of the ones here. Okay, you have expectation of this times product of expectations of these. So here you get a fixed point equation for some kind of nonlinear transfer operator, because you have here the power k. Okay, and so you have to consider this type of map. F lambda c goes to this operator, f of k, and then you use a fancy version of implicit function theorem to show that for the fixed point of this, you have that the map lambda c goes to this c lambda c extends continuously to the real line at energies for small enough lambda. Okay, and then, well, you can express the expectation. So let's forget about this. The expectation of the Green's matrix at site x squared, norm squared. Sorry, in the sense of matrices, so G star G, right? This is the one. You can express as a linear operator applied to this. And so then this also extends continuously. Right, so then this function here extends continuously to the real line, to imaginary part equal to 0. And then finally, using a Foucault lemma argument, you obtain here that you have that the spectral measure has a density in L2 almost surely. Okay, so so basically what's happening is, okay, you have this relation here, and then the imaginary part of this one then is also kind of L2 bounded, and in the imaginary part of this one dE, this measure, when eta goes to 0, converges to the spectral measure, right? But then along a subsequence, you find that this is L2 bounded, and then you have weak compactness in the L2 space, so you have another subsequence where the functions converge in L2, but these functions it converges to, it has to be the density of the limit of these measures. It's absolute continuous measures, and so the limit will be an absolutely continuous measure, which has an L2 density. Okay, so these are the things I wanted to present. And if you have any questions, then we can meet in the discussion sessions.